Hi, we're here with Mike Houston. He is our official OpenCL guy, and he's going to talk a little about what OpenCL is.
So OpenCL has been an effort sort of in Kronos for the last about year and a half. And what it really is an attempt to get an industry standard for doing data parallel computation. And sort of what this sprung out of was the initial GPU style work. So there was Brook, that was originally at Stanford, SH at University of Waterloo. And then as things sort of progressed out of academia and industry, we have Brook Plus here at AMD, NVIDIA has CUDA, but all these represent sort of proprietary implementations of sort of doing data parallel computation. And so what OpenCL represents is an industry standard way to do this. And moreover, as opposed to just targeting GPUs, it targets multi-core CPUs, mobile devices, DSPs, things like the IBM Cell chip. So it's really sort of an all-encompassing standard. And sort of the good thing about that is, so instead of sort of vendors squabbling over what the language is and getting ISVs sort of confused on what to do, there's now sort of one thing to do. So from AMD's point of view, the nice thing about it is that we have multi-core CPUs and GPUs. And so OpenCL is going to provide us a way to allow developers to code up parallel applications that are going to run on whatever silicon we put in a box. So it's kind of neat for us. And because it's sort of a unifying standard, it's going to make it a lot easier for ISVs to maintain code bases moving forward. It's also cross-platform, so it's going to run on Linux and Windows and a bunch of mobile devices. And so that's sort of a large advantage over some of the other ways to do computation on these things.
What kind of hurdle is this going to be for developers to transition into using OpenCL?
Yeah, so it's not that bad. It's a different dialect. I mean, there's minor differences. It's C-based. CUDA and Brook are also C-based, so a lot of that code will move across. Frankly, the trickiest thing on getting something to work in data parallel language or on a GPU is less about the language. It's more about how you adapt your algorithm. So that's where all the sort of thought and effort really goes into. And so frankly, if you've sort of done heavy parallelization work on anything you have, even though you might be switching to a different dialect, you've done pretty much all the heavy lifting. So if you're starting from Brook or CUDA, moving to OpenCL is actually fast and surprisingly direct. That being said, there are a lot of things that OpenCL can do that other languages actually can't do. So besides sort of actually having formal conformance tests and surprisingly strict specification, there's sort of this nice breakdown between sort of code that runs on the device and then code that manages the device. So in OpenCL speak, there's sort of a platform layer, and then there's the device layer. So device layer is where your kernels run, sort of all your main computation. So all those big loops in your app that take 90% of your time, those are the things you put into kernels to run on the device. But sort of the runtime and platform layer has a really advanced queuing system. And so you bring up a device per queue, and you can get these really complex dependency chains going through the queues. So it's really designed, actually from feedback with the game developers, on what a game engine really looks like. They have all these different tasks to complete. Some are data parallel, some are task driven, and OpenCL is designed so all that lives in this queue infrastructure. It's really designed so kind of your entire pipeline of computation in your app is kind of pushed in there. The other thing is that OpenCL is designed to work very well with graphics APIs. So, there's a nice sort of tight coupling between OpenGL and OpenCL, for example. Both done in Kronos. The groups play nice together, so that works. And the vendors on the Windows platform have also been working on DX11 and DX10, DX9 integration with OpenCL. And so, this really is designed sort of for the consumer space, where there's been a lot of push for CUDA and other things to be really sort of HPC focused. And OpenCL is much more designed for consumer space. It's one of the reasons that mobile devices, so cell phones, there's an embedded profile for OpenCL, and that's sort of one of the pushes there. The main goal of OpenCL is to really have ubiquitous kind of computing in a language everywhere.
Right. So you mentioned this is mostly for, or it was designed with a lot of input from the consumer market, software developers. So can you name a few categories of applications that this would be great for, besides gaming, obviously?
Right. So one of the classics is photo and video editing. So there's a lot of things like convolution, things that you're touching a lot of data, take a surprising amount of computation to complete well. especially if you're dealing with really large images or high-res video. It can be surprisingly computationally intensive to actually process an image or process a frame. And so that's sort of one of the initial uses that we expect. There's also other uses that people likely see less directly. So there's been a bunch of companies, there's a few that have already released virus scanners actually running on GPUs. It's just another one of these things where it's a throughput application, it's processing a tremendous amount of data, so GPU is a good place for that. There's simple AI. So that's more of a kind of a gameplay or gaming thing, but there's lots of people who have done artificial intelligence systems, modeling systems, so L systems, which are used in some modeling packages. There's people that are looking at sort of physics as more of a general thing, not just game physics, but applying a lot of techniques that have been proven in game physics to actual professional modeling packages. They can deal with collision and how things really plug together and sort of tracking in that. There's been some initial work, and I hope to see more on actually literal Hollywood rendering and physics and post-processing and other things using this technology. So post-processing has been a big one in for folks like Disney and Pixar and ILM. That's a lot of what they do is compositing sort of computer-generated stuff against live film. This is another thing that can be accelerated with GPUs. Going further, Pixar, ILM, others have shown research on actually using GPUs to speed up their lighting and rendering pipelines. So it's going to be interesting to see that kind of continue within OpenCL. The main thing, though, is that we're kind of in this transition phase where sort of this style of computation, especially on GPUs, just recently exited sort of academic and research and has really just been in industry for a short period of time. And so we're only now beginning to see applications come out. And it's really now with sort of things stabilizing in this realm that we're seeing developers really latch onto this. And we've already seen things where it used to be the vendors would have to really kind of handhold people and help them get through this. And now we get these random reports where somebody has done something really cool, using our GPUs, and we had no idea. So one of them is, we've been working on folding at home for a long time, and so we've been working with Stanford on that. But there's a separate project that we just got a note that a guy was able to do it. It's called Milky Way at Home. And so they use the double precision on our hardware, which is pretty zippy, especially compared to a CPU, to actually do sort of galaxy-style computations. And it was something that we didn't have any interaction with the vendor. They just kind of did on their own. So that was done on Brook Plus. We expect when OpenCL rolls out that because it's public and so many vendors are going to support it, we expect to see lots of developers do things that we never intentioned OpenCL to do. It seems to always be the case. Developers find out neat things to do that we had never really conceived of and really push the limits of our hardware and software.
Yeah, it's going to be an exciting next few years with this coming out.
It's going to be very interesting. We have surprising number of vendors that are going to be getting in. AMD is sort of full push behind this, sort of for CPUs and GPUs. NVIDIA's in the mix. Intel will be back in the mix shortly, having their Larrabee processor. I think this is an interesting thing if you look at sort of what we're able to do. Right now we have the highest sort of theoretical throughputs, the sort of raw brute force horsepower, a lot of things. But sort of having all the vendors get in there and different ways to optimize for their chips and all this, I think we're going to learn a lot as an industry, how things run on everybody's processors, but moreover, how we're going to improve things moving forward. So you have all the hardware coming up, and simultaneously you have all the ISVs latching onto it. So the end of the year is actually going to be very exciting, and then as we kind of roll forward, our hope is that if you look at sort of the game development pipeline, it's sort of 2 to 3 years until technology becomes available, until it can be really used in the game engine. And so that means, basically 2 or 3 years from now, we should begin to see, OpenCL and all the things you can do with it really begin to show up in games and professional apps and consumer apps. And so kind of in this cross phase where you're going to see a lot more sort of interest, interaction with the developer community, and then our ramp up before sort of real products begin to come out. But there are some that we expect to come out at the end of the year, sort of consumer and professional products using things like OpenCL.
Cool. Well, thanks, Mike. This has been very helpful, and maybe next time we can get a drill down into some of the cool applications.
Sure.
All right. Thanks.